Ladies and gentlemen, good day to you all. Today we are going to look at the elementary aspect of organic chemistry. As we can remember generally that we have many branches of chemistry which include organic chemistry, inorganic chemistry, physical chemistry, nuclear chemistry, cosmochemistry, medicinal chemistry, analytical chemistry, and many more. But for the purpose of this discussion, we are going to narrow down into the area of organic chemistry. So ladies and gentlemen, as we can remember, when we say organic chemistry, it means it's a branch of chemistry that deals with the study of carbon and its compound, including the reactions that they undergo. So now, as I defined organic chemistry, as from the screen here, we can see that it's the study of carbon, the compound it makes, and the reaction it undergoes. But ladies and gentlemen, we should know that there are millions of compounds of carbon, but it's not all the carbon compounds that are organic. Like for example, whenever we have a metallic cyanide, that is a metal attached to cyanide, then a cyanide compound, we have the presence of carbon. But the presence of that carbon do not make the metallic cyanide to appear as organic compound. So therefore, generally, it's not all compounds that contain carbon that are referred to as organic compounds. Like for example, we also have metallic carbides. That is, whenever you have a metal attached to carbon, that compound is also not organic. We also have metallic trioxocarbonate like sodium carbonate, magnesium carbonate. They contain carbon, but they are not organic compounds. We also have carbon dioxide and carbon monoxide. Despite the fact that they have carbon, but they are also not organic compounds. So these are actually some few exceptions of the organic compounds. But apart from this compound that I have just mentioned, all the compounds that contain carbon, apart from the exception ones or the exceptional ones, so they are organic compound. So therefore, organic chemistry, it's trying to give the basics idea of the study of carbon and the compound, the carbon it makes, and the reactions it undergoes. Like for example, if we have CH4 is a typical example of organic compound. Like for example, if we have, as I said, CH4 like this, it's an organic compound. And apart from this, we have over 16 million carbon containing compounds, which will be well known. So as of this time around, over millions of the carbon containing carbons are known. So it means that the organic compounds are so numerous, there are many. So as of this time around, 16 millions of them are known. And because the organic compounds are highly rich in carbon to carbon single bond, which has, like for example, the bond energy of 348 kilojoule per mole, and the carbon to hydrogen bond, which also possesses 429 kilojoule per mole of the bond energy, make the bond to be very strong. And this is why the reason why a compound containing carbons are highly stable. So therefore, because of this single bond that exists between the carbon to carbon and carbon to hydrogen, it makes the organic compound to be highly stable. And carbon also, why it is really look at, or it really look nice as a main element in organic chemistry, is it has the ability to form a long chain and the rings, and it also has the ability to form the branch chain, and this is what we call catenation. When we said catenation is the ability of the carbon to form straight chain, branch chain, or ring chain compounds. So that is what you call catenation. So carbon has that property, and this is actually one of the main reasons that make it to appear as a main element in organic chemistry, that is the carbon. So you see, this is a typical example of how the catenation is, that is the chain and the rings exceptional ability of carbon. Like we can see, the first structure is octane. This is the ball and stick structure of organic compound. So you can see octane means contain 8 carbon, and we have ethyl benzene. So you can see it is a benzene ring attached to ethyl group. And we also have isoalcohol, that is a branch is attached to the linear. And we have ethanol. We also have 2-octene, meaning that we have a double bond in carbon 2. Okay, and we also have what we call homologous series. We call it homologous compound. When we said homologous compound, it's trying to give a basic idea of the related compound that have the same functional groups. But ladies and gentlemen, remember, when we said functional group, it means it's an atom, group of atoms, or bonds that determine the chemical properties of the compounds. Like for example, compounds with the same functional group are said to undergo the same type of chemical reaction, while compound with different functional group may undergo different types of chemical reaction. So that is what we call a functional group. But in homologous series, we are talking about the compounds that have the same functional group, but they have different chain lengths. This is a classical example. You see, this is a functional group. Look at the column of functional group. We have hydroxyl group, which is OH group. So a class of the compounds that have OH group is alcohols, or we generally call them alkanol. So you see R is attached to the OH group. R here means alkyl group. And we have classical example, which is ethanol, containing 2 carbon. And this is the ball and stick model structure. So you can see this is carbonyl, also functional group CHO, which is not as aldehydes, or we can call it alkanol. That is the other name for the aldehydes. So you see they all have their functional group. You can see that the functional group between as we can see, the functional group of the alkanols and aldehydes and the last, which is ketones, are different. So that is why you will not accept these 3 different class of compounds to have the same chemical properties because they have different functional group. As you can see, a simple classical examples of the class of compound, like for example, in the alkanols we have ethanol, and for the aldehydes, that is alkanol, we have acetaldehydes. So you see, and for the ketones we have acetone. So you see that they have different functional group. So ladies and gentlemen, I hope you now understand the meaning of functional group. As I said, the group of atoms or atom itself, it may also be a bond, which can be either single, double or triple bond. That is a functional group. So you can see that for this class of compound, the functional group is just a group of atoms. Like for example, for alkanols we have OH, aldehyde we have CHO, then for the ketones we have CO. So this is the examples of different functional groups. As you can see, we have thiols, RSH, we have nitriles, we have carbon to nitrogen triple bond, we have nitro groups, which is R, NO2R, as I said, stand for alkyl group, and we also have aromatic rings. So these are the simple classical examples of the compound, or of examples of different functional group. Then so we are now going to look at the real aspect of the homologous series. So for the homologous series, each member in the series is differ by the next subsequent member by CH2. So since we said by CH2, so it means that between the first and the second member is differ by CH2. Here we can set by 14 gram per mole molecular mass. Yes, if you calculate the molecular mass of CH2, you will obtain 14 gram per mole. So it means that each member differ by the next member by either CH2 or 14 kilogram per mole. And then it can be represented by the general formula. So the member of the same homologous series always have the same general formula. Like for example, alkane. You see, this is alkane CN H2N plus 2 alkane. So all the members of alkanes have the same functional have the same general formula, but for the alkenes we have CN H2N, that is alkenes. So all members of alkenes have the same general formula, and for the alkenes also have the same general formula, CnH2n. So this is a classical example. As you can see, the number of carbon atoms, the watch root, IFAC name, structure, and the molecular formula. So you can see the compound that contains first carbon has a root, that is the word root, meth. So because this is alkane member, so in the meth you will add letter A and E, that is the last three suffix from the alkane, that is A and E. So you see, meth changed to methane, so the structure is CH4 and the molecular formula is CH4. Then carbon 2, the word root is F. So in organic chemistry, understanding this word root is very, very important, because each and every organic compound is attached to this word root dependent on the functional group. So because this one, it has a single bond as a functional group, which is alkane, so that is why after the word root you add letter A and E. So that's why from met you have methane, from eth you have ethane, from prof you have propane, from but you have butane, pent you have pentane, hex you have hexane, hept you have heptane, oct you have octane, non you have nonane, dec you have decane. So these are the structure and the general formula of each and every one of them. You see, this one is also the same based on the number of carbon and the structure. We also have similar chemical properties. Yes, all members of the same homologous series have the same chemical properties because they have the same functional group. So that is why, like for example, for the alkane, because they all have single bond, so it means that they are saturated. So a simple chemical reactions or chemical properties that the alkanes family undergoes is substitution reaction. Because when you say saturated, because of the presence of their single bond, it means that they don't need addition of anything, but you can remove something and replace it with another group. So that is why I said it undergo substitution reaction. And at the same time, they have physical properties that vary in a regular manner as a number of carbon atoms increase. Yes, the physical properties differ from one another because as you go down from methane to decane, the number of carbon atoms increases. So therefore the physical properties also change. Example like the alkanes, you see the physical properties from methane to decane. You also look at the formula. So you see as you are moving down, the number of carbon atoms increases. Like methane has 1 carbon, ethane has 3, then propane has 3, butane 4. So you see the boiling points and the melting point increases as you increase the carbon atoms. You see that the melting point from methane to decane increases from -182 to -30 degrees centigrade, and the boiling point also from methane to decane increases from -164 to 174, and also the density also increases, as you can see from pentane we have 0.63 to 0.73. So you see this is how it increases, or how the physical properties vary as the number of carbon increases. And this is also for the boiling point. We can now see it classically how it increases based on the increase in a number of carbon. So trend in boiling point of members of homologous series: melting point and boiling point increases with more carbon atoms. So as we can see from the previous slides. So why do we have this change? Because this melting point and boiling point increases because of the increase in intermolecular forces due to increase in the number of electrons that are loaded. For example, adding a CH2 adds more electrons. So by this, it leads to the increase in van der Waals force of attractions. So that is why the melting and the boiling point increases, because as the intermolecular forces increases, you need to apply a high or greater force before it boiled and melts. So that is why we have this increase in boiling and melting point. So this is another example how the boiling point increases with increase in the number of carbon atoms. So ladies and gentlemen, I will stop from here, then we'll continue from the next video tutorial. Thank you for listening.